Let's consider a situation where we have two bolted members in tension, where the bottom member has applied force 1 and the top member has an applied force F2. Because each action has an equal and opposite reaction, the bolt is applying a force in the opposite direction that is of equal magnitude to F2 on the top member, and a force in the opposite direction equal in magnitude to F1 on the bottom member. The forces F1 and F2 act over the surface of the bolt hole within each member and cause a stress. These forces also cause a shear force and subsequently a shear stress in the bolt. To solve for the bearing stress in a member, we'll project the curved surface of the bolt hole onto the diameter of the hole. F2 is going to be exerted on this surface, shown by the red shaded plane below with thickness T and width D. The bearing stress is defined as sigma sub B, where B refers to bearing. This is equal to the reactionary force per the area to which this force is applied, which is equal to R per TD, where T is the thickness of the member and D is the diameter of the bolt hole. We'll call this area the bearing area, or A sub B. This, like the other types of stress, has units of pascals. Let's consider the following Pratt truss, made of members of equal thickness, and determine the bearing stress in members AB and AC at joint A, given theta is equal to 60 degrees and the force acting downward on the center of the bridge is equal to minus 1,000 newtons in the y direction. We'll learn how to find these forces in later lectures, but for now we'll assume RAY is 1/2 the applied load F, FAB is equal to 577 newtons, and FAC is equal to 288.5 newtons. Zooming in on the joint we're analyzing, we can see that FAB is acting along two parallel members, so the force in each member is equal to FAB per 2. Remembering that the bearing stress is force over bearing area, and the area over which the force acts is the diameter of the bolt times the thickness of the member, we find that member AB has a bearing area of 4.2 millimeters times 9.5 millimeters, which gives us 3.99 e to the minus 5 meters squared. From there, the bearing stress in one member AB is equal to 1/2 FAB per AAB, or 288.5 newtons per 3.99 e to the minus 5 meters squared, which gives the bearing stress of 7.2 megapascals. Looking at member AC, we can see that the thickness of the members is equal. Since the diameter of the bolt is the same as in member AB, we know that the bearing area of member AC will be equal to the bearing area we found for member AB. We can then calculate the bearing stress as FAC per AAC, which is equal to 288.5 newtons per 3.99 e to the minus 5 meters squared, which is equal to 7.2 megapascals.